Hey guys, Sebastian from Madrigal here. Welcome to this 11th part of the video series where we create a Vulkan renderer for the Basis game engine. So this time we will finally get to fill in this render context VK class. And once we have this, we should have all the major classes in our backend actually working to some degree, which should mean that with a little bit of luck we'll actually get to see things on the screen this time, which is pretty exciting. Right, so let's have a look at the VEC documentation again. I've studied the way that VEC records command buffers, essentially draws things quite a bit through the samples, but let's just quickly review it here. So it is vastly simplified from the normal Vulkan API. So first of all, we need a queue, and we're interested in the graphics queue. So a device in Vulkan can have a number of queues, and here you can see you can have a graphics queue, you can have a compute queue, and a transfer queue. And these are sort of specialized for doing certain things. And in this case, we're interested in this graphics queue, and there's a very handy function here. In VEC for actually you get the device, the queue index, and you get the queue out. So we'll be using this one to get to the graphics queue. And then you have a function called VEC submit queue, which you essentially give it a number of command buffers. So here, command buffers, and you submit to the queue, and then that essentially makes the GPU actually do the work that you want. Then once you've submitted to the queue, you can do a presentation. So VEC queue present, and this essentially lets you put things on the screen. And when you're done with this, you can go back and record another command buffer. So we're going to keep things as simple as we can with this current version of the renderer. Maybe I'll go crazy later on, but we're going to essentially just do the classical thing of rendering to a command buffer every frame, submitting it to the queue, and then presenting it, and that's essentially it. And we need to do a little bit of synchronization here, and this is the part that can be a little tricky to get right, especially if you want optimal performance. We're not going to do the most simple thing we can do, which is essentially this here. You can submit to the queue, you can get a fence, then you can wait for the fence, destroy the fence, and that means that you're done. Instead, we're going to do essentially what I have done on the metal side as well. If you remember, we have this basis VK header, and we have this define VK max frames in flight 3. So that means that we can essentially let's see if I can actually, can I draw this out for you? Right, so we have a timeline here. I'll try to draw that out a little better for you. You have some time. This is divided into some time unit. It's not really that interesting. And you have can get rid of that. We have CPU, and we have GPU. So essentially, the CPU can do a bit of work, and once it has done that work, it will submit it to the GPU. The GPU does some work. And if the CPU, if we do essentially what we did here with the with the wait here. That would mean that when we reach this point, the CPU would only start doing new work when the GPU is done with its work. That's kind of wasteful. So instead we have this max 3 frames, which means that this is essentially like frame 1. The CPU puts together the commands for frame 1, and they're submitted here. So this is the GPU doing the frame 1. Time advances that way, obviously. And then, as soon as we have done that, the CPU can start to put together frame 2, right? And once frame 2 is done, it submits it to the GPU, and then the GPU starts working on frame 2, while at the same time the CPU can start working on frame 3, etc. This is kind of like the ideal case where once the CPU is done with frame 2, the GPU is done with frame 1, and it's not really gonna look like this. Like in practice, it's probably looking something like this, and then maybe the GPU is like doing things a little longer, so that the CPU has time to actually start doing the next frame, etc. Something like this. And there's going to be some small gaps, and we have like 1, 1, 2, 2, and 3. In this case, we have the CPU finishing frame 3 here. That means that it will actually have to wait, because this is now what we're talking about. Like we have the first frame starts here, and the third frame starts here. Well, we're actually going to no, sorry, I was actually wrong. It doesn't have to wait, because it is done with frame 3, so it will go back to writing for the first frame again, because we have 3 buffers. We have 3 max frames in flight. Yeah, so this will actually work. However, if there was the case that the GPU actually spent longer here on frame 1, when the GPU is still working on the data at the same time as the CPU has finished 3 frames, we actually have to wait, because we don't have 4 buffers, we actually only have 3. So we have to sort of make sure that okay, this first frame's data on the GPU is free again. And that is the idea with the max 3 frames in flight model. And that means that the CPU and the GPU can work in parallel. They don't have to wait for each other, but they do have to wait if the GPU is so slow that the CPU runs sort of 2 frames ahead of the GPU. Then we're going to have to wait. But until that, it's fine. They can work in parallel. And this is where synchronization comes in. We have fences, and actually we have semaphores as well. So semaphores is used to synchronize between essentially queue submissions with the same queue or different queues, but essentially like pieces of work on the GPU. And fences are used to sync the GPU and the CPU. So this is what we'll actually want to use to make sure that the CPU doesn't run further ahead than the 3 frames, or the current frame plus 2, compared to the GPU. And fences they're actually kind of simple to use with VEC compared to normal Vulkan. We can see here, for instance, a synchronization primitive can be used between a queue and a host. Host being the CPU, and the queue being the queue and the GPU. In Vulkan, fences is either signaled after the execution of queue submission or unsignaled after being reset. In VEC, fences are never reset. Once a fence is requested, status may be queried or it can be waited on. And you can just get a fence by allocating a handle for it, and you get submit some work and you just give the address of that, and it will actually figure out how to create that fence for you. Then you can wait for it and you have to destroy it. So a lot easier than in on Vulkan, where you actually have to create it by hand. Semaphores, same thing. And we'll get to how to use those. The samples in VEC are a pretty good source of actually understanding how these things work if you're using VEC. Right, so queues, just to go back one more time here, queues are not actually where you sort of add most of the work. Most of the work is actually added to something called command buffer. So command buffers are also a thing in Vulkan, but using them is quite a bit simpler in VEC once again. And command buffers are where we actually record all the binding of resources, drawing things, etc., etc. And as we covered previously, we actually submit a command buffer to a queue. So here was again queue submit to the queue, and we give it a bunch of command buffers. In our case, we'll only ever give it one, but since we have the max frames in flight to 3, we'll actually want to have 3 command buffers. And looking at metal once again, I'm going to copy some ideas from there. But like we started with, like we started this part with, we'll want to have the queue. So VK queue, come on, VK queue, like that, and it is the graphics queue that we'll want to work with. Then we will have the VK command buffers and command buffers, and we'll want to have 3 of them. So basis VK max frames in flight, which is 3, and we will also want to just have a handle to the current command buffer, the one we're essentially currently recording things to. And I want to have those fences that we talked about. So frame fence. Yes. And I haven't actually. This is kind of like me guessing how this would work, because the samples, unfortunately, they work a bit differently. In this case, most of the VEC samples actually like pre-record their command buffers, which is like how one would ideally do this, but almost no non-trivial game will be able to pre-record their command buffers. They're gonna the frames change so much that you're essentially going to have to re-record most of them all the time. And due to the fact that the samples use these pre-recorded command buffers, they don't really use fences in this way. I'm hoping this will actually work out fine and result in somewhat good performance, but we'll see. Again, the point of this video series is really to sort of just to make something that we can work on and improve on later, just to get things on the screen, hopefully more or less correctly rendered, but the performance might be kind of lackluster. Just like in Vulkan, I'm gonna get a pointer to the current render target, because that is typically something that we'll want to have, and we actually need to pass it to the bind function in the pipeline. Right. So, what next? Well, let's actually initialize these guys. So, so render device, as always. No, it's called device VK. Device, and the graphics queue, that would be a null VK null handle at this point. Command buffers and fences are arrays. Current render target would be a null pointer. Why are you being sad? Oh, this was the thing that I wanted. Command buffer is VK null handle and render target is null, and then we'll do like a for uint 32 I is smaller than max. What is called basis VK max frames in flight. Like so, and we'll just do command buffer is VK null handle and frame fences I is also VK null handle. It's not the current command buffer, it's command buffers. Okay. So due to the fact that VEC claims to handle these fences itself, you just essentially have to give it a fence handle, and then when you're done with it, you destroy it. I'm hoping this will be a pretty easy way to do basic synchronization. And we'll want to go probably all the way down to create, which is here, and we do the thing we looked at earlier, where we do like get device graphics. So compute queue, we want the graphics queue, device VK, get VK device. Q index, I'm just going to use 0, and M graphics Q, right? Right. And then we can allocate the buffers, the command buffers, and I think you can actually do multiple in a like with one in one go. Right, so you have the queue here, we did that already, and then essentially take this guy, copy it in here, and remove the line numbers. So graphics queue, that would be that guy. Command buffer count is the basis VK max frames in flight. And we'll put them here. And of course we'll want the device there as well. Right, okay. And we've done the creation. Let's do the destruction. I learned this from my previous stint with Vulkan, that whenever you destroy something central, you should probably wait for the device to be idle. So let's just do that here. We're gonna get actually to object destruction. That is going to be a problem with the current way we have things set up. I'm thinking that I'm gonna have to implement some kind of delayed destruction thingy, but we might not have to do that for this video series, but it's something that I'm gonna have to do sooner or later to make sure that things are properly cleaned up, because you can't really if we go back here, if we are, let's say, at this point, right, and the CPU has just submitted the frame buffer, the work for frame 2. The GPU has not yet started working on it, so it has all these pointers that it's going to work on. If we destroy everything at this point, then the GPU will be the rug will be pulled out from under the GPU, and that is that's not good. That's not something you want. So destruction is it's not super easy. Okay. Okay. Actually, maybe we don't need a for loop here. Can we actually, if we we do like VEC. It was allocate command buffers, so it's probably free command buffers, right? Yes, it is. Indeed. And you can do the same thing. Yeah, cool. Okay, so mDevice VK, get VK device. The count is still the same, so basis VK max frames in flight, and this is the address of that, but this is an array, so I'm not actually supposed to put the ampersand there. Right. So let's actually have a look and see that this... Oh, I should put an assert there before I forget. So basis assert f, that result is VK success. Result. Does this actually... that's a void. So that shouldn't fail, apparently. Failed result is %d. Like so. And now we should be able to run this. Yes. And what do we have? We have a success. Excellent. Okay. So, how does this context thingy actually work? Well, we do have create called. That is something we already saw. And then what will start to happen is that we'll call begin frame. We'll call I think present, and then end frame. And those will be called in that order, I think. So let's try that out. Let's put some breakpoints here. We will have begin render pass. We have a couple of overloads, and then end render pass. Those will be called in between, but I want the actual order of these guys verified before I go any further, because they will manage this whole synchronization thing for us. Let's have a look. So we have begin frame as expected. Then I think present is going to be next. Yes. And then end frame. And then we go back to begin frame. Yes. So begin, present, end. Begin, present, end. And this just keeps happening until we shut down the app. So what we will do here then is that in end frame is where we will actually take this frame index, which we've talked about before. Frame index is the number that starts at 0, goes up to 2, and then back to 0, because currently this is 3. And frame number, oh, not that, plus is what I wanted. Frame number increases linearly, right? Let's make sure that, well, we don't need to make sure. That's so simple stuff. And when we end frame, we should have a current command buffer. This should not be VK null handle, but we want to actually set it back to VK null handle. Right. So now if we run this, we should get an assert failure because we never set that. And as soon as we enter the main loop, the expression is false. It should not be null, and we get here. Okay. So when we call end frame, we're essentially done with the whole thing. We should have actually submitted and done all the things that we are interested in. Okay. So it goes to. It's only logical that if you call end frame and then the next thing that is called is the begin frame again, then at this point we should not have a command buffer. So this should be null. VK null handle. Yeah, my microphone is kind of covering up the view to my keyboard, so that's a bit annoying. And the current command buffer will be m command buffers, and we will use this frame index, which is 012, 012, 012. So that is the command buffer that we want to use for that frame. And then we have this frame fences thing. So if frame fences for the very same command index is not null, that means that we have actually, there has been a previous frame because we have gotten a fence from VEC earlier. And how do I know that? Well, it is written here. Fences. Right? Right. So, in contrast to Vulkan, the application responsibility for resource access synchronization is partially alleviated by VEC. Blah, 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 blah. Fences and semaphores are not explicitly created by the application, but requested when calling VK submit or VK present, as previously described in the queue submissions. So, if we call VK submit, then we just hand it like a fence. A fence, yes, and it will fill it in for us, and we can wait for it, and then we need to destroy it. All right. So if we have a fence here, and we can do something like this. So that would be mdevice vk get vk device. Same thing here. This would be the address of m fences frame index. Then we have wait all, and we have a timeout, and we probably don't want any of those. Okay, and then we want to destroy this fence, right? So we want to do that, and then we want to set it back to vk null. VEC expects us to destroy that fence when we are done. We'll get a new one in present on the next frame. Okay? Okay. And so what we actually want to do in present then is we want to, let's just make a list for ourselves here. So end the command buffer, and then we want to submit the command buffer, and then we want to present, and I think that's it actually. And the semaphores will be used, or a semaphore will be used to sync between the submission and the presenting. That's how the samples did it, so let's do it in the same way. And I think that yeah, I think this queue submission is where we'll get our fence. We'll see. Okay, so let's try to fill this in. So we have vk result. Result is VEC end command buffer. We haven't actually begun a command buffer yet, but we will do that in a sec. But it doesn't want any parameters. That's interesting. Let's have a look at what the docs say. I'm just gonna copy this here in the meantime. So VEC end command buffer. What does the docs say about this guy? Okay, it's the same thing as previously, where like if you called begin command buffer, then you can, on that same thread, you can you can just call things and they will be associated with the command buffer. So that's okay. That's fine. We'll probably begin the command buffer like here after this fence, I think. Okay, and then VEC submit info was the thing that they submit. No? Yes, submit info. Submit info is something we'll need to fill in to do the submission. And what has this guy eaten? Okay. Okay. Okay, so we'll want to have, we want to have a VK, VK semaphore, there we go. Semaphore, and we can set that to VK null handle for now, because now we'll actually want to, so command buffer count is 1, that's easy. Submit info, p command buffers is the address of current command buffer. That's the command buffer we'll want to submit. We want the signal semaphore count to be 1, and we want the signal semaphores to be address of semaphore, I think. And then we'll want to do some things, and we'll copy these, and we'll actually want VEC Q submit, and we can copy that there, and then we can look at what it expects, and it will probably expect, no, it doesn't expect it. The device expects the Q, so that would be like mgraphics Q. Submit count, that would be 1, and submits is this guy, so it's submit info. And then here we have the fence, right? So for some reason it's not giving us part of submit info, it's giving us part of the fence. Maybe you can have multiple submit infos, but just one fence. So this would be like address of m-frame fences, frame index. Let's make sure that builds at least. We haven't done anything stupid. It builds. Okay, so what I think we're doing here, and what I hope we're doing here, is that we're ending the command buffer. We're allocating a place to put a semaphore, right? We're telling the queue that, hey, we have one command buffer, it's this one, that we want to submit that. And we have signal semaphore count. This guy also had wait semaphores, right? We don't set any of those. We set the signal semaphore count. So it basically means that when this queue has been submitted, when the work has been done, we want one semaphore, this guy, to be signaled. And in addition, we also have this fence here, which we want the fence to be set, I think is the correct term. And once the semaphore has been signaled, we can actually proceed with the presenting, right? So, how do we present things? How do we present? Present all the things. Queue presentation. Okay, we can copy this. It looks pretty good and tasty. Looks pretty good and tasty. And we don't want the signal semaphore, I think. Stage color attachment output bit. Okay. I don't exactly know what this is, but let's leave it as it is. For now. Okay, so what we will need the swap chain, and we will need the source image. Well, we get the GFX API swap chain here, so that's good. We can cast that to a swap chain VK, And then we can probably get both the swap chain and the source image out of that. So let's do that in a second. Signal semaphore count. We probably don't need any signal semaphores at all, but we do need a wait semaphore count. So presenting and submission, or like queue submissions and then presenting, even though they're just sort of called one after the other, you still have to tell the GPU to like wait for one before doing the other. That's how it works. So the semaphore that we want is actually this guy, and that would be that guy. And then we need to do that, and then we need to do this. And so on. Yeah. Oh, we have wait semaphores twice now. Get that away. Take that away. Take it away. So wait semaphores is the same thing that we have here as the signal. This one signals, this one waits for the signal, right? Make sure we do the work and then we present the work. Okay. I hope. Wait semaphore count 1. Images and swap chains, we need to figure those out. Swap chain count 1. Wait destination stage mask. I hope this is correct. I don't know exactly what that does. I can look at the samples if that's not the correct one. I should probably look at the samples to figure out what exactly that does. Okay, but in the meantime, swap chain VK. Swap chain VK. So we need to get the swap chain out. It's that guy. We can just do. Everything is public now. Actually, everything is public now. I probably don't. I can't probably do that. I just need to make it like this. I think those need to be protected because they're like coming from the base class. Right. So we have the swap chain. But how do we get the actual image then? Can we get the image out of the swap chain? Well, we can use the render target, and the render target. We'll just do the same. Actually, we have friend classes here, so we don't need to do that. We can get the images out of there. Yeah. And for this, we actually only have one. It's this guy. That's the image we want, because VEC makes this easy for us. We only need to actually allocate one image, or at least that's what we're doing right now. So this is the image we want, and that's the swap chain we want. So let's make a new method here, something like void. Maybe we don't need to do that even. Maybe we can just. We need to do something like this. We need to do swap chain VK. VK swap chain is static cast into swap chain VK swap chain. Right, and then this swap chains. This will be the address of M swap chain, and images will be the address of render target M color. No, M color. What? Come on. Render target is the correct type. This is a friend of the render context VK. There we go. Now we can access it. I just want to make sure that this actually works before I make any other complex things. And it builds. Okay. You get rid of that one. Let's put some sort of limiters here to sort of signal where these things are happening. So we have first one is this one, then we have second one, then the third one. Whoop. And what it is that. Okay. Okay. Whew. Jeez. I do hope this works out. Render context VK. So then we had this ending of the command buffer there, but we don't actually begin. And command buffers they use this kind of state machine thingy where they are like in a certain state. I think once we have, there was something called a reset. What was it called? Reset command. Oh, it's not listed there. It's probably reset command buffer. Exactly. Yes. So we need to reset a command buffer because most likely we have actually used this. It's only on the first frame that we haven't actually used that for something. And resetting a command buffer that's already reset is not a problem. So we'll do that. We reset the command buffer. So here we determine which command buffer we want, and then we store it here. Then we figure out, do we actually want to wait on the fence? And we wait for the fence there, obviously. So when we get past this point, then we're ready to begin recording into this command buffer. Do point out in the comments if I'm doing this wrong, but I hope this will work out. So then now we can begin. So begin command buffer, and again we want the current command buffer and flags usage flags. One time submit, render pass, continue bit, simultaneous use bit. I think it's one time submit bit because we're just gonna reset. We're gonna record our things into it. We're gonna submit it. And then we're gonna reset it again. Like that. Does that make sense? I think so. Okay. I guess we should like technically be able to run this now without it just completely blowing up in our faces. Can we though? Ooh, we get a black screen now. How exciting. And we're running. Hey, exciting things. Exciting stuff. Actually shut this down. Does it properly shut down? Yeah. Okay. So here we have actually, this is one of the problems that I'm probably not going to actually solve in this video series, but I'm going to have to solve later on once I figure out how I do it. So this is the problem here. Cannot call VK destroy image on VK image that is currently used currently in use by command buffer. Yeah. So again, is this kind of thing? Well, it's no longer active. Anyway, yeah, it's the thing I talked about earlier, where you can't actually destroy things that are in use by the GPU. So what I might want to do here is actually in the GFX API object, you have like a release here, and this is how we kick off destruction from the core library side, which calls then destroy on the actual objects, and then as you've seen in almost all the classes, we like destroy just then goes and calls something like destroy frame buffer here. We need to actually delay this by like 3 frames or something. Like we could sprinkle the code with these with these calls to wait device idle, and that would block until the GPU is no longer doing anything. But that's not a very good solution, because if you destroy like a texture that you no longer need while the game is running, you don't want to wait until the device is idle. You just want to delay that a little bit to make sure that it's no longer in use or something. I'm gonna have to figure it out. But I think, yeah, we're no longer actually gonna be able to cleanly shut down the game during this video series. I'm gonna get this, if I shut this down, I'm gonna get this validation error happening. But then we can just click exit and it will shut down anyway, so screw you, Vulkan. That's what I wanted to do. Okay, anyway, this looks good because we are sort of stepping our frames now, and we're not getting any validation errors while we're actually doing that. So I think the waiting on the fences is working out. Destroying it there, yeah, so we're not leaking any things. Although we had that pretty big memory leak earlier, and I checked, it's coming from our Vulkan backend, so it's probably something that VEC is doing internally. I'm gonna have to look at that as well. Okay. What's next then? So we have begin frame, we have end frame, we have present, we have begin render pass. That looks like a pretty good next thing, and this is easy. This is just render pass. This is what every backend does. It just does default params, and then it calls begin render pass with the render target and the default params. And that's it. It's just giving it to this guy. And so here is where we'll want to actually grab a hold of this guy. Again, this is something that we do in almost all, or essentially in all the backends. We just cast it to the correct type, and we render target like this. And to begin a render pass in VEC, I think we call something like command begin render pass. Is it command begin? I know it's a command. And okay, it's a command begin render pass. Cool. VEC render pass begin info. Okay, so let's do VEC render pass begin info. Begin info. And what does begin info want from us? Right, so this is now where I was I'm kind of proud of myself, because this is where let me call it make. Render target VC. Go to there. Make render pass begin info. This is the thing that we did in the previous part. Man, this guy is really not liking me doing that. What's going on here? Why is it giving me errors all the time? I cannot assign the entity of. I don't quite believe you, but apparently that is the case. Current render target, what is that? That's a pointer to render render context. Oh, yeah. Render target VK. Now we should be good, and we are. Right, so maybe we now get some better IntelliSense, and we do. So we give it the begin info, and we give it the params. And so if you don't remember what this does, this does the load, store, clear, don't care, this whole business. Essentially just fills in one of these guys, because it knows, the render target knows everything that it needs to know here, and it gets the params for the things that it doesn't know, so we can use that. We fill in the attachments, and we fill in the frame buffer and all of that. So now we should be just essentially ready to begin. So address of begin info. And I think that should be it. And in the end render pass, we do a VEC command end. No, render pass. Yes, we do. We don't need to tell it anything. It's again these things that it sort of keeps track of what you have begun on this thread. But we do, however, want to probably set this back to null pointer. Because the current render target is only valid during a render pass. We begin it, we set it, we end it, we clear it. And here I have some commented out things. These are commented out on metal as well. We don't need to actually care about these. I had a system earlier where you could clear render targets, so the colors and the depth stencil separately, but now we just do it through these render pass params all the time, so it's kind of easier. Okay. And binding the pipeline state should be pretty damn simple as well, so we just cast it to a pipeline state VK pointer, right? And then we call bind. And the render target is the current render target. That's it, because we did so much work here already. We're doing all of this. Actually, if we run it now, does that breakpoint that we left there, does that actually get hit? Does that actually get hit? It does. Hey. Hey. And we're not even receiving any validation errors. That is awesome. Okay, cool. So that's binding pipelines. Yeah, this thing has a lot of functions, methods, but most of them are actually really short. So binding a vertex buffer then. Okay. That would be the next thing to do, and this is like VEC command again. We do everything through commands now. Bind vertex buffers. Okay, binding count, buffers, and offsets. Right. Okay, so essentially what we want to do here is we want to cast it into a buffer VK, like something like that, and static cast it into a buffer VK, vertex buffer, like so. And out of this we get the VK buffer. VK buffer. I'll call it B. That would be buffer VK get. And this is now where we do the whole get buffer page thing, where we do all of this crap, which you can find out more in the part about buffers. And what do we want? So we have 2 units buffer device size. Okay. VK device size. That's probably just like a size T or something. It's a unit 64. Okay. Offset. Now it's already called offset there. It's called O, and cast it into that, and that would be offset. Now we should have everything we need. So this will be slot, and that's 1, and that's B. Oh, that's address of B, because you can pass multiple, and that's address of O. Yep, I think that's it. Then if we do multiple, so basically these guys are the ones that we need. So let's create a bunch of them. VK buffers. How many should we reserve? Maybe 16 or something. I don't want to go too crazy if we so that we don't blow like the cause a stack overflow or something. Offsets 16. And yeah. Maybe we should assert here that the buffer count is less than or equal to 16. Okay, so for uint 32, I is 0, I should be smaller than buffer count. We once again do this, we do this, and we do this and that. And we do VK buffers. I is buffer VK get buffer page. So we do essentially the exact same thing we did above, but just as an array. Just do group and offsets I. So like you need to give an offsets and I. Yeah. You need to give an array of offsets as well. And then we do the same thing as we did here. But that's obviously buffer count, and that's VK buffers, and that's VK offsets, right? And that's actually called start slot because we'll be binding a bunch of them. Okay, good. Let's build to make sure that we haven't done anything stupid. All right, still building. That's a good sign. That is a good sign. And then for the index buffer, we probably have something like bind index buffer. Auto completion, making things difficult again. Okay, buffer offset and index type. VK index type. What is that? VK index type. It's probably like 16 or 32-bit. Yep. Okay. So type. This would be. We have to get it out of the description, right? What is this? This is like the const gfx API buffer description. Call it desc, as I typically do. Index buffer get description, and then in the description we should have this type thingy. So if that's 16-bit, then we'll do 16-bit. Otherwise, we'll do 32-bit. Yeah, that's good. And we'll want to do this probably. Index buffer instead. Cool. And this would be buffer VK get buffer page. Right, and now we just want, we don't need to cast it here because we're not giving like addresses. So we can just give offset like that, should be fine, and then type. Like here, for example, you give actually an address, so I can't give like an address to an uint32 when it expects the device size, but here I can give it because it's not an address, it's just you can just bind one index buffer at a time anyway. Okay, we're getting there. We're like almost at the drawing functions. Let's just do this. Let's just do this. Whoa. Okay, VK viewport is the thing that we want to fill in here. I happen to know that because I just looked at a thing earlier, and so we have viewport dot top left x. And we have VPY, which is viewport dot top left y. Width is viewport dot, no, not that, viewport dot width, and we have height, which is viewport dot height. We have min depth, which is viewport dot min depth, and we have viewport dot max depth, like so. And then there should be a command for this, so it's VEC command set viewport. Right, and we looked at this earlier, so this is actually setting, that should be 0, that should be 1, and this should just be the address of VP. There's the VEC command set viewport state, I think it was called, but this just sets like the number of viewports. I don't think we shouldn't need to do that unless we actually have several of them, which I currently don't. So, and what was the type that this actually expected? So command set scissor is VK rect 2D, okay? So VK rect 2D is our, and scissor offset X is scissor rect left. Like you always manage to just do these things slightly different than everyone else, and then scissor left top and scissor dot extent dot width is scissor rect dot right minus scissor rect dot left, right? Again, point out my mistakes in the comments if you spot any. I think it's bottom minus top. That's typically what I use. I should know my own conventions, shouldn't I? Again, let's use 0 and 1 and the address of scissor and build that. And we're golden. Okay, the drawing commands should actually be really simple. These should just be essentially like one-liners. I had a look at the drawing commands earlier, and this should just be super easy. So vertex count is just vertex count, and index count is 1. First vertex is first vertex, obviously, and first instance is 0. So these become gradually more complex. So VEC command draw VEC command draw in text. Yes, that's the one. So index count, instance count is still 1. First index is first index. Offset is 0 and first instance is 0. And I think this one is that, but was it this one? Vertex offset, yeah, so that's the base vertex. And now we come to the instanced ones, and we just used exactly the same ones, but we actually have some more data for these guys now. So vertex count is like vertex count per instance. Instance count is instance count. First vertex is first vertex. And first instance is first instance. Super easy. Yeah, so just forwarding those parameters to VEC. And we have index count per instance, and we have instance count. Then we have first index, vertex offset, that's base vertex, and that is first instance. I use almost the same names as previously. Just making sure I got all of those in the correct order. I think I did. Okay. So, yeah. We have the binding of things left. We don't need to do the unbinding. I'm actually not going to do the generate MIPS here, even though it's sort of used for a few effects. But I'm hoping I don't have to do that. And these are not required for the Vulkan backend. They are just actually implemented only on D3D11. So this part is getting pretty long already, and I think once we actually get these bindings done, we should be able to actually draw things, or almost ready to be able to draw things. So let's end this part here, and in the next part we only have these methods to fill in. We should be able to draw, and then we can actually reserve some time. I want to like almost start with rendering things for the first time in the next part, because I'm sure there'll be lots of small things to fix. So we didn't quite get to actually rendering today, but we got to actually pumping the frames, and we got a black screen instead of a white screen. So exciting times. Next time we'll definitely be rendering things, unless there's something catastrophically wrong with what we've done so far. So stay tuned for the next part, and remember to like, subscribe, hit all the things and the buttons and everything, and I'll see you in the next one. Bye.